am from Technical Lyceum of Kyiv Polytechnic Institute, and the topic of my work is Characterization of Graphene by Raman spectroscopy. Nowadays, a great attention is paid to study and application of nanotechnology. Nanotechnology is able to create many new materials and devices with a vast range of applications, such as in medicine, electronics, and biomaterials and energy production. Nanotechnology needs some materials which have appropriate properties. In this respect, carbon nanostructures can be very useful because of their crystal structure. And now I want to draw your attention to the main allotropes of carbon classified by the nature of the chemical bond between the atoms. sp3 hybridization. Diamond is a metastable allotrope of carbon, where the carbon atoms are arranged in a variation of the face-centered cubic crystal structure called diamond lattice. sp2 hybridization. Carbon nanotubes are allotropes of carbon with a cylindrical nanostructure. Graphite is an electrical conductor, a semi-metal. It has a layered planar structure. In each layer, the carbon atoms are packed in a honeycomb lattice with separation of 0.1418 nanometers. And the distance between planes is 0.335 nanometers. Fullerene consists of different numbers of carbon atoms, and starting from 20. The most known is T60, also called Buckminster fullerene. Graphene is one layer of graphite. Graphite and also graphene and diamond are crystalline forms of carbon. Nanotubes and fluorines are molecular forms of carbon. And in the picture you can see red, it's a structure of diamond. Near yellow, it's graphite, it's fullerene, and dry is nanostructure, nanotubes. Graphene can be described as one atomic layer of the layered mineral graphite. In recent years, great attention is paid to study and application of graphene. Graphene itself is a monolayer of carbon atoms packed into a two-dimensional 2D honeycomb crystal structure. The Nobel Prize in Physics for 2010 was awarded to Andrei Geim and Konstantin Novoselov for groundbreaking experiments regarding the two-dimensional material graphene. Applications of graphene in technology. There are a lot of applications of graphene, such it can be useful in creation of hypersensitive sensors, chemical and biological. It can be helpful in miniature high-capacity capacitors, transport touchscreens, and even sometimes in medicine. There are some photos of graphene. On the left you can see a few layer graphene under the optical microscope, zoomed in 7 times. And on the right is some packages of graphene containing a few layer graphene and graphene oxide. Physical properties of graphene. High-quality graphene is very strong, nearly transparent, and excellent conductor of heat and electricity. Measurements have shown that graphene has a breaking strength over 100 times greater than a hypothetical steel film of the same thickness, with a tensile modulus stiffness of 1 terapascal. Also, graphene has a record thermal conductivity about 5,000 watts per meter Kelvin. Electronic properties of graphene. Graphene can be described as a semi-metal or superconductor as a zero-band gap. Conduction band and valence band of graphene merge into specific points on the edges of the brilliant zone. Brilliant zone you can see on the left down picture. As a result, the effective mass of carries close to zero. Theoretically, graphene must not conduct electrical current. However, in practice, it has a high conductivity. On the right, you can see an image of conduction band and valence band of the electric or semi-metal, and down conduction band of metal or graphite. Raman spectra of graphene. For characterization of graphene, the most useful and informative technique is Raman spectroscopy. Any carbon material, nanotubes, graphite, fluorines, nanowires, or graphene can be effectively characterized by this method. Raman spectra of graphene was registered by Renshaw in the Raman microscope with wavelengths of laser excitation about 185 nanometers. You can see it on the right. The main feature of the Raman spectra of graphite structure as well as graphene is the so-called G mode, and now you can see it on 1592 centimeters minus 1. This mode with lines of E2G, E1G, A1G symmetry in the gay point of Brillouin zone correlates with the ordering of crystal lattice of graphite. The second characteristic mode of graphite-like materials is the so-called D mode, with a A1 symmetry that characterizes the disorder of graphene layer lattice. It refers to rings breathing vibration of graphene layer in the key point of Brillouin zone. The second order mode of this vibration, so-called G prime or 2D, was registered at 2615 centimeters minus 1. In graphene layer, the position, line shape, and intensity of G prime band could be used to determine the number of layers in the graphene sample. In this sample, it's about 7 or 8 layers. It's not the greatest graphene. Characterization of Raman spectrum of graphene. The D band, for historical reasons, is known as the disorder band. This peak is due to lattice motion away, its presence between 1270 and 1400 centimeters minus 1. It depends on the excitation of wavelength. And it indicates defects or edges in the graphene sample. In fact, a definitive explanation of its origin depends on excitation wavelengths is derived from the double resonance theory originally proposed by Thomson. In this theory, the intraband phonal scattering of the electron requires momentum that is easily taken up by defects, which is why this band was first observed in defective crystals. Characterization from a spectrum of graphene, G band. The G band is the main spectral feature of graphene. It is derived from in-plane motion of the carbon atoms and appears near 1508 centimeters minus 1. It is extremely sensitive to strain effects and is also a good indicator of the number of graphene layers. As the number of graphene layers increases, the G band position shifts to lower frequencies, following a 1/n dependence on the number of layers n. Here you can see it. Blue is if it's graphite, B layer it's green, and red it's a single layer of graphene. There is no significant change in spectral shape. However, despite this sensitivity to the number of layers, it's preferable to use the 2D band for reasons described in the next slide. The G band is also sensitive to doping, and both the frequency and the line widths of this peak can be used to monitor the doping level. The 2D band, also called G prime, is a second-order two-phonal process. It exhibits an unusually strong frequency dependence on the excitation level due to a double resonance process which links the phonon wave vector to the electronic band structure. This feature appears at approximately 2,700 centimeters -1 for a 514 nanometers laser excitation, and can also be used for the determination of number of graphene layers. However, its behavior is more complex than the frequency shift observed for the G band. That is why it's better to use 2D band to determine the number of layers. Feature 7 on the right shows the dependence of 2D band on the number of layers. While a graphene monolayer can be fitted by a single Lorentz sand peak, a bilayer requires 4 Lorentz sands, which are related to the 4 possible double resonance scattering process, when only one is possible for the monolayer. Here, 1 layer, 2 layer, and graphite. When the number of layers increases, the number of double resonance process also increases, and the spectral shape converges to that of graphite, where only 2 peaks are observed. Also, figure 8 shows dependence of 2D band intensity from the number of graphene layers, with lasers excitation 514 nanometers and 633 nanometers. Another explanation of 2D band or G prime band. Some scientists assert that the G prime and D prime band are all second order process. It is said that despite G prime band being sometimes referred to as the 2D band, it is not the second order mode of the D band. It is also mentioned that the G prime band appears in a perfect graphene sample, while the D band is absent, since the G prime band has nothing to do with defects of graphene. Another first order band is the low frequency E2D mode, involving the weak inter-layer interaction, so usually it can be observed on the Raman spectrum of graphene. You can see the spectrum the standards received, and G prime or 2D prime and D prime. But now the assignment of 2D band is under discussion, so we can't say exactly. There are Raman spectra of graphite, multi-wall carbon nanotubes, and graphene. With all these all the spectra were registered with a wave of laser excitation 785 nanometers, but it's better to use 514 because it's better see the 2D band. Raman spectra of carbon nanotubes are sometimes presents different features, being all sensitive to such as the radio breathing mode RPM. It's one of the greatest distinguish of the Raman spectra of carbon nanotubes and graphene. Here you can see a Raman spectra of single-wall carbon nanotubes, which was registered with the wave of excitation of 532 nanometers. Comparison of Raman spectra of graphitic carbon structures, graphene and nanotubes. Difference between Raman spectra of graphene and spectrum of nanotubes is obvious. 2D band of graphene is more intensive than in carbon nanotubes, and the shape is different in the D band and 2D band. In conclusion, I would like to say that graphene is a new nanomaterial which may particularly replace silicon in microcircuits and computer chips in the future, help in creation of hypersensitive sensors, transparent touchscreens, and even help in medicine. In order to better understand its quality characteristics, fast, reliable techniques that deliver the right property measures are needed. Raman spectroscopy has emerged as a key technique for studying this exceptional material. That is why it's very important to know Raman spectrum of graphene and difference between it and another graphitic carbon structures. That's all. Thanks for attention.
Okay, someone question? Okay. So, just such question. If you compare intensity of G band and D band for different materials, can we connect these intensities with amount of defects in such materials, or it's not so strictly?
I would say it's not with the defects, but with number of layers. D band, it's better to determine the doping level in graphene or carbon nanotubes.
Can you say a little more about you? How old are you?
I am 14. I am from Kiev. I am studying in technical team of Kyiv Polytechnic Institute on physics and math form. I like physics, and in the future I would like to become someone in such way.